the algebra is similar. The question doesn't seem like it's a constrained optimization question, but it is. It's simple. The question seems pretty simple. It says, find the point on the circle that's closest to this point 1, 2. It doesn't even seem like a Lagrange multiplier question. I want to be on the circle. X squared plus y squared is 45. Okay. At the same time, I'm on that circle. I want to be as close as possible to the point 1, 2. So here's a circle of radius 3 root 5, right? The square root of 45. And then here's my point 1, 2 inside the circle. And I want to be as close to that as possible. Now close as possible, I need to set up a function that measures distance. So I can make that, if I want to be as close as possible, I want to minimize distance. And so I get a generic point that is on this circle. So I go grab a point on this circle, generically call it x and y, and I represent its distance to our given point, which is 1, 2. And so just this formula, we do x minus 1 quantity squared and y minus 2 quantity squared, and technically we should take the square root for distance. But hopefully you've seen this where the way the square root function grows, if we can minimize what's underneath, we'll be minimizing the entirety of the root function. And so that's what we're going to end up doing. It's so much easier not to have that square root there algebraically in solving the equations. And so we're going to minimize the x minus 1 squared and y minus 2 squared. This doesn't have to be done this way. You can do this without Lagrange multipliers. But I want to show you it's solved using Lagrange multiplier. Okay. All right, great. So here's what we're going to do. What's the constraint? What needs to be true? What's holding you back? What's stopping you from using every point possible in the plane? The constraint is that you have to be on the circle. The constraint is what we call G, and we want to take it so that it's set equal to 0. So the 45 that's on the right-hand side, we just ship it over. So here's my function G of x and y. It's x squared plus y squared minus 45. And I'm going to create this function capital F, which is lower f minus lambda times g. So I take my f, lower f, and then I take lambda times my g. Okay. And I'm just going to take partials of this. Partial respect to x, partial respect to y, and as you see, when you do the partial respect to lambda, you end up with the opposite of all the terms that are there, and that would be basically the same thing as moving everything over to one side, but it's set equal to 0, so it's making sure that your constraint is being solved. Okay. And here's the problem with this whole method of Lagrange multipliers. It's the algebra. It's not the calculus. It won't be that we'll have difficulty taking these derivatives. It's the idea that we have to solve these equations simultaneously. We get led to many different cases that are possible. We have to basically consider all cases, and sometimes that can be difficult. And so what we want to do is there's no set way that I can say that you should do every problem this way when it comes time to solving the algebra of taking these partials and setting them equal to 0. Some questions have different things in them that the other questions don't, and you just want to be able to I like to be able to give you something to say that every problem can be done this way. I can give you something that I can at least say most problems can be done this way. And so I take my x partial, so I'm looking at this capital F function. I'm going to take an x derivative. So my first part of f here, I'm going to get 2 times the quantity of x minus 1. And then my other x partial derivative term is going to come from the g, and I'll get minus 2 lambda x. And so that's my x partial. I'm going to set that equal to 0. My y partial would be, bring down the 2 here, 2 times y minus 2 quantity, and then minus my 2y lambda. Okay, I'm going to set these guys equal to 0. And also, I need to do my lambda partial, which is basically negative signs on everyone that's in the parentheses there. And here's the issue. I need all these guys to be 0 at the same time. So fx needs to be 0, fy needs to be 0, and it's just a formality. F lambda equals 0 just ensures that you're on the circle. And so there's many cases that comes out of that. Let's go with doing it as we work here. So all these guys need to be set equal to 0. But all of our attention is put forth on the x and y partial, because the idea of lambda being equal to 0 just ensures that you're on the circle. Okay? And my advice is this, that's going to help you through most problems. I can't say all. Your goal should be, with fx and fy, sometimes fz also, to get some relationship between your variables. Find somehow a function that says, why is this on x? Because if you get that, then you can take that into your constraint and you can solve for the, for the x. It turns your constraint to be starting from 2 variable, then to be a single variable equation that you can solve. So the goal in whatever algebra you decide to do should be to somehow figure out a way to write y as some function on x. I don't know, call it h or something. That should be your goal somehow. And it comes different for different problems, and it may not even work for some problems, but keep that in mind, and it'll get you pretty far. Okay. Some people would say that there's like a case-by-case scenario that you should try to solve, but this goal here can help you through mostly everything. So what does it mean? Fx equals to 0. Do you notice anything from these two terms? The thing about I like being set equal to 0 like this is that we can factor out things that are alike. And so really, I'm just going to have this 2 can come out, and I'd have x minus 1 minus lambda x. So I'm looking at 2x minus 1 minus 2 lambda x. I'm sorry, my lambdas will look like x's. I apologize. And I'll just take the 2 out. That's about all I can do. It leaves me with x minus 1 minus lambda x. Okay, so if my x partial is going to be 0, it's going to be because what's in the square bracket is 0. The 2 doesn't matter. That's all I can say out of that, is that x minus 1 minus lambda x is 0. That's the information I should take out of fx being set equal to 0. What I do with that, if I have this goal in mind, then we should see what I'll do with that. But let's just do the exact same motions to the f sub y. There's no set way to do this. I'm just giving advice, basically. Kind of best practices. And so we'll do the same thing. Notice similarities in the equations so that you can exploit that, essentially. And so I noticed that I can do the same kind of factor out of 2. And they look similar. And so I can exploit that similarity maybe. And my goal is to get some kind of relationship between x and y. And so the 2's don't matter here either. And I'm looking at the fact that y minus 2 minus say it again. Okay. All right, so this is what I'm looking at. And I want to relate these to each other. I want these to be true at the same time. Okay. Them being true at the same time should tell me something about x and y in some kind of way. And so I see x appearing twice. I see y appearing twice. So maybe I could take advantage of that. I can move the 1 and the 2 over, respectively. I can say that x minus lambda x is 1, and y minus lambda y is 2. Okay. Now here's where you get into trouble. If ever you try to divide by anything, you just need to consider what would happen if that was 0. Most people forget this. It probably won't even mean anything to you, but you just need to consider it. So I am now going to factor out an x. and factor out a y, and I'll have these identical terms, 1 minus lambda. Okay. And so I'm going to have the fact that x times 1 minus lambda is 1, and y times 1 minus lambda is 2. And I would like to divide by that, to say x equals this and y equals that. But I just need to stop for a second and say, well, what would happen if I couldn't do that? What would happen if the lambda was 1? So it ends up in this sort of case. Either lambda is 1, and I can't divide, or pretty much I can then say what I really want to say, which is basically that x is, that y is pretty much twice x. See, what I want to do next is divide by lambda. 1 minus lambda, sorry. I want to do that next. And so it would tell me exactly that x is 1 over 1 minus lambda, and y is 2 over 1 minus lambda, or the fact that y is twice x. Okay, that's what I was looking for. That was my goal. But it can't be true if lambda is 1. So let me go down the road. It might not mean anything to me at all, but I need to go down the road that says, what happens if lambda is 1? Technically, to get full credit, I got to go down that road and see what that means to me. Okay, but all of our fruitful information is going to come from the fact that y is twice x. Okay? All right, let me add a slide here. Let me see, here's what happens when I do this. Oh, boy. All right, geez, I will. So, I'll end up keeping this. It looks bad when I do that, but then I go and add a slide. And let's do our two cases. Either lambda's 1 or y is twice x. Case 1. Lambda is 1, and case 2 is that y is twice x. One of these has to be true. All right. So let's go down the road of lambda being equal to 1. What happens there? Oh, boy. Let's see here. I want to keep all this. Let me read this here. Yeah, kind of. Okay, that's good. So what happens if lambda is 1? What does that say about x and y? Let's take these boxed off equations here. If lambda is 1, what does that mean here? If lambda is 1, right? Most times, I can't say all, but most times, one of the cases ends up as nonsense, not meaning anything to you. This is true. It has to be true. This equation needs to be true. But if lambda is 1, then this equation is not true, right? This equation, if lambda is 1, let me write it on the other slide. If lambda is 1, my x's cancel out, and it says negative 1 is 0. If lambda is 1, my y's cancel out, and it says negative 2 is 0. Okay, that's the consequence of lambda being equal to 1. We get nonsense. Okay, the equation that said that x minus 1 minus lambda x equals 0, with lambda being 1, leads to nonsense. It says that negative 1 is 0. That right there is enough. But even overkill, this guy too. Lambda being equal to 1 on that one too. My y's cancel. And so, but I just officially, I do need you to go down that road though. It's unfortunate, but I do need you to consider it. And so it says that negative 2 is 0, and it's not. And so this then means that lambda cannot equal to 1, which won't stop you then from being able to divide. And so we must be in the case where y is twice x. And if that's the case, then go into your constraint. If y is twice x, go into your constraint. the fact that x squared plus y squared needs to be equal to 45, knowing that y is twice x. Exactly twice x. Y should be double whatever your x is. So x squared plus 2x quantity squared is 45. You have 4 of them and then 1 of them, altogether conveniently 5 of them, so that when you divide by, you end up with a perfect square, and we get that x has a choice of being either plus or minus 3. Question, yes?
Yeah. So
I'm sorry, what's your name? Sorry, no.
Logan.
Logan.
Yeah. If case 1 turned out to be true, we would not need to explore case 2, right?
I guess they both could be true at the same time. Nothing to stop that.
Divided by 0 error in the one equation, so we have lambda or over lambda minus 1.
Right. Right. Just because the division by 0 ends up giving you something doesn't mean that the other guy can't be true too.
So we need to explore both cases.
Yeah. It's unfortunate. If you went through this whole problem and you never considered case 1, I really should give you mostly every credit, possible. I feel bad, like, marking it down and you get everything right and you give the right answer and it's all written up nicely. I feel bad not giving you 10 out of 10. Okay. I would say most, I can only take off a point, really. This thing isn't really worth much to you, but you just need to fully consider it, though. Okay? And so x is plus or minus 3, making y plus or minus 6. In that order. So the point 3, 6, and the point negative 3, 6. 2 points came out of this, but in the end, we'll see that one's the biggest distance away from that point, and the other is the smallest distance away from that point. Max and the min thing that we talked about. Okay, and so, but had there only been one, we'd be sure that whatever came out would be the maximum. Okay, so there's that, and then we end up with. I guess I'll keep this too. I like this way of writing it up. Let me get rid of all this. Sorry, and you just get the nice, pretty way of writing it up. You'll get 20 for your f before taking the square root. If you take both of them being positive, you'll get 80 if you take them both of them being negative. And here are the points being plotted, of course. And we could have just, just by the visual of this whole thing, said, what the answer was that we were seeking. Of course, is the 3, 6. But I just want you to see that when there is 2 that come out, that one's the maximum of that and one's the minimum of that. And the actual distance, they didn't ask us for this, but the actual distance, don't forget that you simplify things by taking rid of that, getting rid of that square root. And so the actual distance is 2 root 5 there. And it makes sense. There's a line here. Y equals twice x. If you were to draw the line in, y equals twice x. It would intersect at those 2 points. It would go through your point 1, 2, and that distance there would have been 2 root 5. So there's that question worked out with Lagrange multiplier, and I don't have case 1 being considered here. I wanted to make sure that I rewrote these slides to now include both cases being considered. Questions on example number 1? Yes, Nico.
Why can't you relate x and y using the third function, the f lambda?
Why can't you relate x and y there?
Yeah.
Oh, you can. You could say that x squared is 45 minus y squared. It's a true statement. You have to incorporate that into the fx and fy, and there's nothing to say that won't end up giving you information. You definitely could do that. Like I say, there's no set recipe as to what you should follow to do the algebra, and that's another technique you could do. I saw another hand. Hi, what's your name? Kevin.
Where's the first one? That x minus 1.
Okay, we wanted this. Okay, it was subtle. They said closest. So closest we relate to distance, and then distance we go with the distance formula. Distance between what 2 points? My given point 1, 2, and this random point out in space x, y. So x minus 1 quantity squared, y minus 2 quantity squared, but I don't want to deal with the root being there, so we can minimize what's underneath. Okay? All right, great. One last. Oh yeah, sorry. Go ahead. What's your name?
Alan.
Alan.
Yeah, so Lagrange multiplier, does that just refer to like lambda or like the entire way of solving?
The entire method, the entire way of solving this. Okay, yes, lambda is an L, and I don't know if that's the reason why, but no, it could be any constant we want. This whole technique was developed by Lagrange, and it gets his name, and this whole method of solving a constrained optimization question is this. The multiplier definitely is the lambda, but the method is titled Lagrange multiplier. No. One more quick. I forgot your name. I'm sorry. Manuel.
What if we got one answer from this? That would be the minimum distance or maximum?
If we got, I know the question is asking us to minimize, and I know I said if I got one answer, it would be maximum. But maybe what I should say then is that if you get one answer, you just make an argument as to what that answer really is. Is that answer a maximum? Like you need some kind of analysis at the end there, just some kind of maybe couple sentences to answer what it really is to you.
No, yeah, I mean like, what if you got one answer?
What I'm saying is that you just need to argue why it is what you think it is, and not the other one. You're going to need some kind of argument. Here's the problem worked out. I don't know if I can blow this up. Here's the problem worked out. Oh, it's just using different algebra. Using the same attack at it. I think it's just using different algebra. Some people like this idea of, okay, I see lambda in this equation. I see lambda in this other equation. Let me solve for lambda in both. Why not? And set them equal to each other. And it works for 95% of the problem. It works out nice. And it's a bit more messy, but here it is. Here you can look at it on your own. But this is the solve for lambda in one, solve for lambda in the other approach. But once again, it leads to many cases of worrying about division by zero. I don't think I do my whole full case analysis on this thing either. Yeah. If you're solving for lambda, you're going to have to take into account that these guys could be zero, and then that's a possibility that these guys could be zero, y could be zero, and x could be zero. You just need to argue that out. I do it here. If x is zero, it leads to the nonsense that you had from before. Yeah. So I don't write it out as cases, but anyway, you end up at the same place. So if you like the solve for lambda approach in each, then definitely I would say try that as your first attack. It's just a quirk in the problem that we came up with this nice y equals 2x, without much trouble doing the way that I had done it when we wrote it up. Okay. So